students. Now I'm going to take moving coil galvanometer, right? Moving coil galvanometer. So galvanometer as a instrument, right? Okay. Yes. Shall we go to the topic? Okay. Yes. Yes, we are going to discuss following topics. The topics are introduction of galvanometer, principle, construction, working, and applications of galvanometer. Okay. Yes. Yes. Introduction. Small introduction. Yes. For the galvanometer. Okay. You see this. So galvanometer is an electromechanical instrument which is used for the detection of electric current through the circuits. Okay. So what is galvanometer? Galvanometer is an electromechanical instrument which is used for the detection of electric current through electric circuits. Okay, right? So it is an electromechanical device, right? Okay, yes. See the next. Being a sensitive instrument, galvanometer cannot be used for measurement of heavy current. So we can't use, yes, for heavy current, measuring a heavy current, right? And at the same time, we can measure very small current by using galvanometer, but the primary purpose of galvanometer is detection of electric current. So what is the main purpose? Detection of electric current, not measure of current, right? So with the help of galvanometer, we can detect the what? Yes, electric current. That means in a circuit, when the if in a electric circuit, the electric current present or not, yes, verified with the help of which one? Galvanometer. So we can't measure the amount of current, right? Yes, because the amount of current measured by ammeter. Okay. Yes. See, what is galvanometer? So galvanometer is an electromagnet that interact with a permanent magnet. Okay. The stronger electric current passed through the electromagnet, then the more is interact with permanent magnet. Okay, so galvanometers are not used as a gadget in cars and many other applications. Okay, it's very simple. The greater amount of current passed to the wire, copper wire, the stronger the galvanometer interact with the permanent meter. Okay, so that see this. It's a diagram. Yes, small diagram for galvanometer. The parts of this galvanometer is, this is needle, and this is measuring scale, meter scale, and this is the coil, copper coil. This is the one end of the coil, and this is the another end of the coil, and this blue is color part is permanent magnet. So this side act as a south pole and this side act as a north pole. Okay, and this is the needle attached to one spring. So this is galvanometer. So galvanometer is a device to detect the electric current in a circuit. Okay. Yes. Working principle of this galvanometer. The basic principle of galvanometer is PMMC. What is PMMC? Permanent magnet moving coil. PMMC. Permanent magnetic moving coil. That is the principle. Because of, with the help of magnet only, that's why we call permanent magnetic moving coil. The galvanometer works on the principle of conversion of electric energy into mechanical energy. That is very important term. Conversion of electric energy into mechanical energy. Yes. When a current flows in a magnetic field, it experiences a magnetic torque. What is that? When a current flows in a magnetic field, it experiences a magnetic torque, right? If it is free to rotate under a S controlling torque, it rotates through an angle proportional to the current flowing through it, which is one current flow through it. Okay, so this is the principle of what? Galvanometer, right? Yes, so this is that moving coil galvanometer diagram. Yes, so this is the leveling screw, this is the leveling screw, this is the bottom, that is base, and this is screw, and this is that top screw, right? So this is the magnet, this one and this one magnet. This magnet is act as a north pole and this magnet act as a south pole, and this is the, which is one deflection cage, and this is the coil. Yes, coil, and the coil is attached to the one is spring, metallic spring. It's made up of brass, so one made up of brass, right? See, this is that exact, yes, moving coil galvanometer picture. See this is the positive and negative terminal, and this is the needle. This end of the needle is connected to the spring, and both sides magnet will present. When the current flow through the coil, yes, because the coil in an uniform magnetic field, no, so it experiences a torque. Due to the torque, the needle, yes, get deflected. Okay, right, based on the direction of flow of current, right? See this is the measuring scale. This is what? Measuring scale. Okay, right? Yes. Construction, which is one construction of galvanometer, right? Yes. A moving coil galvanometer consists of rectangular coil. The coil is PQRS. PQRS of insulated thin copper wire. The coil is nothing but which wire? Copper wire, thin copper wire. Yes, yes. The coil contains a large number of turns wound over a light metallic frame. Yes, light metallic frame. Okay. The same time, a cylindrical soft iron core. Cylindrical soft iron core. That means small, yes, cylindrical piece of rod placed symmetrically inside the coil. Inside the coil. Yes. The same time, the rectangular coil is suspended freely between two pole pieces of horseshoe magnet. It is not a bar magnet. It is which magnet? Horseshoe magnet. Horseshoe magnet? Horseshoe magnet. Right? Okay. Yes. See this? This is the, yes, measuring scale, and this is the horseshoe magnet, right? And this is the which one? That cylindrical body, that cylindrical core. This cylindrical core is surrounded by copper coil. Yes, thin copper coil. Yes, with a number of turns, right? And this is the horseshoe magnet. And this is the soft iron core. This is the soft iron core. This is the spring, and the one end of the spring attached to the spring, right? This is the current flow. This is the one end of the coil, and this is the another end of the coil, right? See this, the one end of the rectangular coil is attached to one end of 5 strip of Prosbon wire. Which wire? Prosbon wire. See, this is that which wire? Prosbon wire. This is the spring, right? And lower end of the coil is connected to hairspring, while it's almost made up of phosphor prozone. Yes, okay. If this coil suspension, yes, strip is window is attached, at the same time a small mirror is attached in order to measure the deflection of the coil. The small mirror is attached, yes, in order to measure the, which one? Attached to measure the deflection of the coil. Yes. Or other end, the mirror is connected to the torsion head T. This is the torsion head T. This is the mirror. This side above this one, mirror is attached. Then the strip W and the spring are connected to the two terminals. Okay. See this? Again I'm telling. See this? This is the south pole and this is the north pole. This is the two horseshoe magnet. And this is that, which one? That torsion head. And this is that bore, cylindrical core. And this red lines are indicate the what? Coil, copper coil. Which coil? Copper coil. Right? Again I'm telling. Yes. The cylindrical core placed between two pulses of two horseshoe magnet. And this core is surrounded by copper coil. Yes. Which coil? Copper coil with n number of turns. Right? See this? The upper end of the rectangular coil is attached to one end of the strip. One end of the strip. Right? Of phosphor boson. Right? And the lower end of the coil is connected to hairspring. It is made up of phosphor boson. Right? Okay. Yes. In freely suspension is window is attached. A small mirror is attached to measure the deflection of the coil. Which is the mirror? See, this is the M is the mirror is attached to the coil. The other end is connected to torsion head. The other end of the mirror is connected to torsion head. Then the window and the spring is connected to the terminals. Which is terminals? This is TS now. So this is the terminals. And the torsion head and this lower end is connected to the battery. Yes, we are giving electric field. Okay. So the LS is leveling screws. This L is what? Leveling screw. Again I'm telling what is T. T is a torsion head. What is TS? T is the terminal screw. And what is M? Mirror. What is NS? Pole pieces of magnet, horseshoe magnet. What is LS? Leveling screw. And what is P? Q, R, S? Rectangular coil. Right? And B, PBW, that is phosphor boson wire. Right? Which wire? Phosphor boson wire. Okay. Yes. Now this is now we are going to see the working of which one? Moving coil galvanometer. Which coil? Moving coil galvanometer. Right? Now consider a single turn of rectangular coil. Yes, single turn of rectangular coil PQRS. Which is one? PQRS. If you consider only single turn. So the length is L and breadth is B. See this? The length PQ and RS both are equal. That is L. Right? And the breadth PS and QR. That is B. Right? And let I be the current flow through the coil. Which coil? This PQRS. Then the horseshoe magnet has semi-spherical magnetic poles which produce the magnetic field. Right? If the current flow through the coil PQRS, the same time the horseshoe magnet has semicircular space, therefore this horseshoe magnet produces magnetic field. Okay, and due to this field, the side of which one? QR and SP, they are parallel to the magnetic field. They are which one? Parallel to magnetic field. See, the blue lines indicate the magnetic field. The magnetic field starts from north pole to south pole. Therefore, see this magnetic field produced in the horseshoe magnet. Due to this one, the sides QR and SP are parallel to magnetic field. So it experiences no forces. It experiences any force? No forces in this side, right? But at the same time, the sides PQ and SRS always parallel to magnetic field, it experiences a force. Sorry, always perpendicular to the magnetic field, it experiences a force. So due to this forces, torque is produced in this area. Torque is produced in this area. See this, when the coil in a magnetic field, no, what will produced? Magnetic field is produced. At the same time, in a magnetic field, a force is experienced. Magnetic Lorentz force, no, the same here. Okay, the force is experienced. See this, when the coil flow to the this coil, yes, P, S and Q are parallel to magnetic field. So this side no forces experienced. But if you consider PQ and RS, some force will be experienced. That force is perpendicular direction. That is FPQ and FRS. So these sides are experience of force. Due to this force, torque is produced. Therefore, immediately the coil get, yes, which one? Experience the torque, so get deflection, right? The coil is attached to one small, yes, needle, no, the needle get deflected, yes, through which one? Scale, right? So torque is experienced, okay, which is when torque is experienced. So this time the hairspring get tighter and reach maximum deflection. After this one, due to the restoring, yes, coil, yes, that is restoring couple, we called as restoring couple, and the coil again get deflected in opposite direction, get in opposite direction, okay, right? So when the current flow to this rectangular coil, PS and Q are sides, no forces, and PQ, SR side experience a force, that force acting in perpendicular direction and opposite to the magnetic field, therefore torque is produced, right? Now come to the torque experienced by the coil. Torque is tau. This torque is depend on number of turns of the coil and the amount of current I and the area of the cross section of the coil, and B is the magnetic field, and sine pi, yes, the sine angle between the force and the magnetic field. Yes, due to the torque, it create the restoring torque in the coil. What is restoring coil? Restoring torque, tau is equal to K into alpha. So K is the restoring torque per unit twist. Okay, so when that equilibrium position, this both torque is equal, therefore NBIA sine pi, which is equal to K into what? Alpha. From this when I am taking I, which is equal to K into alpha divided by N AB sine pi. So here sine pi can be eliminated by using the radial magnet. Which magnet? Radial magnet. Okay. Yes. Again, see this in our book. Force upwards, force downwards. So see this PQ RS side experience of force, right? And this the deflection will be created, deflection couple this side, right? Two forces in opposite direction. The same one, see this is the core and this is spring, this is the coil. The coil, the spring is attached to the one magnetic needle, right? So when the current flow to the coil, what will happen? Torque will be experienced due to the torque experienced. Yes, the spring will be goes on one direction. Due to this, the needle shows deflection, right? So torque is made by the coil is tau, which is equal to NIAB sine theta, and restoring torque in the coil is tau, which is equal to K theta, right? So if it is I, the current I is equal to theta into K divided by NAB, the same as previous equation. theta is the deflection per unit twist. Deflection per unit twist. Therefore, I is equal to theta into k divided by NAB. K is constant and divided by N is the number of turns. A is the area of rotation. B is the magnetic field. Okay. Yes. See this another is diagram. This is the north pole and this is the south pole, and this is that coil and this is soft iron core. So PQRS lies along magnetic lines of force whichever the position of the coil comes rest in equilibrium. The angle between the plane of the coil and the magnetic field is 0. Magnetic field is 0, right? I said no. Sine pi is equal to theta. That is angle between the normal plane of the coil and magnetic field. See the red lines is that coil. So coil plane, and this is the magnetic field. So the theta is angle between the normal plane of the coil and the magnetic field. So it is always perpendicular. Therefore sine pi which is equal to sine 90 degrees equal to 1. Therefore, you are taking I which is equal to k into theta, no, previous case. Therefore, theta is equal to 1. Therefore, k divided by NAB into alpha. Yes, that is equal to R. Otherwise, I is equal to G into A. So, G is the galvanometer constant. What is constant? That is k divided by NAB. K divided by NAB. Galvanometer constant. Yes, k divided by NAB. And the same time galvanometer has sensitivity because it's very sensitive instrument, no, that's why yes it has sensitivity. There are two sensitivity, one is current sensitivity and voltage sensitivity. With sensitivity, current sensitivity and voltage sensitivity, right? Yes, I'll give you the what is sensitivity and what is voltage sensitivity. Okay, yes. See this sensitivity of galvanometer. The galvanometer is said to be sensitive if it is shows large scale deflection, even though a small current is passed through it normal its or small voltage is applied across it. Now come to the current sensitivity definition. What is current sensitivity? It is defined as the deflection produced per unit current flowing through it. Deflection produced per unit current. So is that S for sensitivity, I is current, therefore current sensitivity. Deflection per unit current. Deflection is theta divided by current is I. From the previous equation, I which is equal to K by NAB, no, therefore K here NAB, right? Therefore is which is equal to I by G, because G for what? Galvanometer constant. See this. So see this galvanometer constant, right? Therefore what will come? This I 1 divided by G. It's a reciprocal of constant. Okay. Yes, the current sensitivity is 1 mark. The formula is also 1 mark, right? Next, voltage sensitivity. Yes, before that, in current sensitivity, the current sensitivity of the galvanometer increased by some following factors. The factors are increasing factors. The factors are, if you are increase the number of turns, the sensitivity also increases. And if you are increase the magnetic field with the help of size of magnet, the sensitivity also increases. If you are increase the area of the coil, the sensitivity will increases, right? But if you are decreasing that, which one? Voltage, what is decreased? The sensitivity also decreases, right? See these three important factors by increasing current sensitivity of galvanometer. Okay, yes. Next, voltage sensitivity. So this voltage sensitivity is defined as deflection produced per unit voltage. Deflection is theta and divided by voltage applied, that is V. So Vs is voltage sensitivity. Vs which is equal to theta divided by V, right? So V is equal to theta. According to Ohm's law, V is equal to IR. Therefore, IRG, G for galvanometer, right? So theta by I. What is the formula? Previous formula, NAB divided by K, no? The same way, NAB divided by K into RG. From this one you are taking, yes, NAB divided by K is equal to 1 by G. Therefore, 1 divided by G into RG, which is equal to Is divided by Rg, because 1 divided by G is equal to what? Is, current sensitivity. Therefore, Is divided by Rg, right? G for resistance for galvanometer. Okay, so this is that voltage sensitivity of which one? Galvanometer. Voltage sensitivity of galvanometer, right? Okay, yes. Their applications. So galvanometer is a type of ammeter and yes, is an instrument for detecting and measuring electric current. It is an analog electromechanical transducer that produces a rotatory deflection of some type of pointer in response to electric current flow through the coil, right? The terms has expanded to include uses of same mechanism in recording and positioning and is servo-com mechanisms equipments. So most of the used in X mechanical equipments we are using that. Which one? Moving coil galvanometer, right? Okay, yes. So followed by moving coil galvanometer. Example problem 3.29. Just follow the question. The coil of a moving coil galvanometer has 5 turns. So turns is nothing but N, right? And each turn has effective area of 2 into 10 power minus 2 meter square. So area A is equal to 2 into 10 power minus 2. And it is suspended in a magnetic field, yes, whose strength is 4 into 10 power minus 2 Weber meter power minus 2, right? So magnetic field is B is equal to 4 into 10 power minus 2, right? Okay, if the torsional constant K of the suspension wire is 4 into 10 power minus 9, so K value 4 into 10 power minus 9. Okay, got it? Yes. See the questions. We have to find out three things. One is find its current sensitivity in degree per microampere. Micro means 10 power which one? Minus 3, right? Micro, sorry, 10 power 6 minus 6. Okay, right, and calculate that voltage sensitivity of the galvanometer for its to have full scale deflection of 50 divisions for 25 is millivolt, 10 power minus 3. Okay, yes, and compute the resistance of the galvanometer, right? See this solution. I already said number of turns is 5 and the area of fraction 2 into 10 power minus 2 meter square and magnetic field is 4 into 10 power minus 2 Weber meter square and torsional constant is K is equal to 4 into 10 power minus 9 Newton meter deflection per unit. Now first we have to find out current sensitivity in micro. Micro means 10 power 6, right? Current sensitivity. Now, from the current sensitivity formula, I is equal to NAB divided by K. It is direct equation. Therefore, N value is 5 and A value is 2 into 10 power minus 2 and B value is 4 into 10 power minus 2 and divided by K value 4 into 10 power minus 9. Therefore, 5 into 2 are 10 into 10 power minus 2 here. 4 into 10 power minus 2, 4 cancel. You will get 10 into 10 power minus 4 divided by 10 power minus 9. If you are simplify, you will get here 10 power minus go to that side, 10 power plus 9. So remaining 10 power 6. So the answer is 10 power 6 divisions per ampere. So current sensitivity is 10 power 6, right? And second one is voltage sensitivity. If the voltage sensitivity is Vs, which is equal to 50, yes, 50 divisions divided by 25 millivoltage, that is given, no? Yes. So 50 divided by 25 milli into 10 power minus 3, therefore we'll get 2 into 10 power 3 divisions voltage inverse, right? So here 10 power 3, 25 1 times and divide by what's 2 times. Okay, so if 2 into 10 power plus 3, here 1 by 2, that is go to this side, 2 into 10 power plus 3 it will come. Okay, yes. The last one is resistance of this galvanometer. From this SR, which is equal to IS divided by VS. The resistance of this galvanometer is ratio of current sensitivity and which sensitivity? Voltage sensitivity, right? Therefore, 10 power 6, that is which sensitivity? Current sensitivity, okay. And divide by voltage sensitivity, 2 into 10 power 3. Therefore, you will get 1 by 2 into 10 power 6 already is there, in 10 power 3 go to that side, 10 power minus 3. Therefore, you will get 0.5 into 10 power plus 3 ohm. And 10 power 3 is kilo. Therefore, the resistance, galvanometer resistance is 0.5 kilo ohm. So, from this one, we calculated current sensitivity, voltage sensitivity, and the resistance. Do you understand? Any doubt? Okay, next one. Next problem. The resistance of moving coil galvanometer is made twice its original value in order to increase current sensitivity by 50%. Which percentage? 50%. Will the voltage sensitivity change? Right? That is the question. So if so, by how much? How much change? Okay. Yes. Yes. The solution. The voltage sensitivity formula, we know that Vs equal to Is divided by R. See, if the resistance is doubled, the new resistance will be formed, that is new resistance is R dash is equal to 2 into R, because doubled the original resistance, that's why 2R. Then the current sensitivity is also doubled, that means changes. Therefore, the increase in current sensitivity I am taking Is dash, because previous case Is is the sensitivity, but some increasing in current sensitivity, no, that's why I'm taking Is dash, which is equal to 1 plus 50 divided by 100 into Is. Sir, how it came, sir? It's very simple. See the question. See this 50 percentage. So percentage we know that, no, divide by 100, that's why yes, see this 1 plus 50 divided by 100 into the current sensitivity. Therefore, if I am simplifying, what I get, 150 divided by 100, that is equal to 3 by 2 Is current sensitivity. If the current sensitivity increases, the voltage sensitivity also yet what? Produce. Therefore, new voltage sensitivity is Vs dash. That is nothing but current sensitivity and divide by what? Resistance. From this one, therefore, Is dash. What is Is dash value? 3 by 2 Is divided by 2R. The resistance, no, 2R, which is equal to 3 by 4 Vs. 3 by 4 what? Vs. Okay. At the same time, the voltage sensitivity decreases. If you are using this one, the voltage decreases. Voltage sensitivity decreases. Now, then the percentage in voltage sensitivity. We have to calculate the voltage sensitivity percentage. How to calculate? It's very simple. Vs is voltage sensitivity minus Vs dash. What is Vs dash? 3 by 4 Vs. And what is Vs? Is this value. And divide by Vs. Divide by what? Vs into 100. Into 100. So it is given already 50 percentage. And yes, Vs dash is given 3 by 4. If you are substituting in this equation, you will get 25 percentage. You will get 25 percentage. That is the percentage of change in which one? Yes, voltage sensitivity. Okay, students. Okay. Yes. Conversion of galvanometer into ammeter. Conversion of galvanometer into ammeter. The galvanometer converted into two types. One is ammeter and also which one? Voltmeter. Converted into which one? Converted into voltmeter and yes, ammeter. Right? Yes. This is for yes, their diagrams. Yes. Okay. Yes. Just you should know this topic. Okay, students. Okay. Clear. But we'll discuss these topics in next class. Okay, students. Okay. Yes. So today class is over, right? Okay, students. We discussed moving coil galvanometer principle, construction, working, applications, right? Okay, students. Clear? So this moving column galvanometer is very important 5-mark question. So in this question there are two important questions. The questions are current sensitivity and voltage sensitivity and their formulas. Okay, because followed by this topic only conversion of which one? Ammeter and voltmeter. Okay, students. Clear? Yes. Okay. See you on next video. Thank you, students.